Thank you very much. First, I'd like to thank the organizer for giving me the chance to talk in this conference. It's my great honor. So for the talk, this talk is going to be on the interplay between C-star algebras and topological dynamical systems. And for C-star algebra part, that's this Z absorption. And for the topological dynamical system, that's going to be the zero mean dimension. This talk is based on several works with George Eliot of University of Toronto. So let's start with C-star algebras. What is a C-star algebra? A C-star algebra. So I'm giving you an abstract definition. A C-star algebra is a Banach algebra, means that it's an algebra and it's also a Banach space. So there is a norm. It's complete. And also there is a star operation. The norm of A times B is at most the norm of A times norm of B. And moreover, this Banach star algebra satisfies this C star identity, means that the norm of A star now is exactly the square of the norm of A. And this is a defining property of a C star algebra. This abstract definition and the basic example of a C star algebra are the algebras of bounded linear operator of a Hilbert space. In the finite dimensional case, we can look, for example, the algebra of n by n matrices. They form an algebra, actually form a star algebra. You look at the conjugate transpose. And the norm here, we should look at the operator norm rather than other norms. And in the infinite dimensional case, it's see if this A is a bounded linear operator acting on Hilbert space, you automatically have this identity. And it turns out that those are basically all the C-star algebras. So any C-star algebra defining abstractly in this way actually is isomorphic to some norm-closed self-adjoint subalgebra of B of H. So this is the algebra of bounded linear operator acting on some Hilbert space. So concretely, a C-star algebra is an algebra of bounded linear operators on some Hilbert space. But in general, if you start with an abstract C-star algebra, then this Hilbert space, the choice of this Hilbert space is highly non-canonical or highly non-unique. A special class of C-star algebra is the class or the category of commutative C-star algebra. Suppose A, B equal to B, A. If we look at a commutative C-star algebra, then turns out that they are canonically isomorphic to this function algebra. The function of continuous functions on complex valued, continuous functions on some locally compact Hausdorff space. So a commutative C-star algebra basically is talking about some locally compact Hausdorff topological space. And in general, a C-star algebra might not be commutative. So a slogan in the commutative C-star algebra is that what is a C-star algebra? They're basically a non-commutative topological space, because in the commutative case, that's exactly the topological space you are talking about. So this is a C-star algebra. Now let's yes.
The slogan first.
I don't know who first. No, it's I learned this when I was a student. So, so the next, so now let's turn to the topological dynamical system. So a topological dynamical system consists of a topological space, and we are looking at a compact Hausdorff space. We want to look the unit of C algebra. So here we look at a compact Hausdorff space together with a group. And this group acts on this space X. So for each group element, you can regard it as a homomorphism on the space X. And the composition is compactable with the group multiplication. And this group in this talk, let's assume the group is a discrete group, countably infinite, and let's also assume it's amenable, because the C algebra in this talk are going to be amenable C algebra or nuclear C algebras. And also, let's assume the space is separable. Let's not talk about huge spaces. So some more terminologies. We are not going to look at all topological dynamical systems. We are going to look at the minimum one. A dynamical system is called minimal if there is no non-trivial subsystem. So means that you look the action on the space X, the only closed invariant subspace are the trivial ones, either the whole space or the empty set. Nothing really in between. So your equivalent way to say that is that all the orbit are dense. Minimal, and we also only look the free dynamical system. Free just means that you look the orbit of any point X, then the orbit is exactly a copy of the group. So the stabilizers are trivial. So we are going to look at the minimal free topological dynamical system in this talk. So C algebra and the dynamical system, which now here is a chain connecting such thing. So from let's start with a dynamical system. So a space and a group action. As we said that C algebra is a non-commutative version of a space, but at least you have a space, then you have canonically you have a C algebra. So from this X, then we have a C algebra. C of X consists of all the complex valued continuous function from X. But then there is also a group and acting on the space X. Then this group actually acts on this C algebra. And now we want to put all the information together to have a bigger and more complicated or more interesting C algebra. We do it in the following way. So we have a new C algebra, and what are the elements of this C algebra, or what are the generator of this C algebra? First, it contains a copy of the space. So in other words, it contains all of the continuous functions on the space X. So it has a copy of C of X, and it also has a copy of the group in terms of the unitaries. So for each group element gamma, you have a unitary U gamma. A unitary is like a unitary matrix. You satisfy the relation U star equal to U star U equal to identity. This copy of the unitary, the group, actually is a group representation. You look at U gamma 1 times U gamma 2, you get another unitary, and turns out that exactly the unitary corresponding to gamma 1 times gamma 2. So you have a copy of the group inside this C algebra, and the relation between the this copy of the group and the copy of C of X is this. So you look at the inner action of the function by the unitaries. That's exactly the given action. The given action of gamma on the space X. So in this single C-star algebra, it encodes the space X, the group, and together with the action. You look at the universal C-star algebra generated by those functions and the unitaries. That's a cross product C-star algebra. And in this case, it's also called a transformation group C-star algebra. And you can really think the general element of this algebra as the functions or the polynomials over the group with the coefficients in C of X. You look at all of the polynomials and how you multiply those polynomials, they should satisfy this relation. Then you take a closure. There is a way to put a C star null, then you take a closure. So this is the this is our C star algebra out of this dynamical system, and we want to look at the structure of this C star algebra and see if we can recover some information of the dynamical system or not. So since we assume the dynamical system is free and minimal, then this C star algebra turns out it's simple because it's minimal. If the action is free, then the ideal of this C star algebra is one-to-one correspondent to the closed invariant subspace. But there is no non-trivial one. Then this algebra actually is simple. It's like the algebra of n by n matrices. There is no non-trivial ideals, and it's unital, separable, also amenable. This amenable C star algebra, this amenable group. Stable and finite means that, well, in this case, it corresponds to the existence of the trace. Because this amenable group, then you are going to have some invariant probability measures that give you a trace on this C star algebra. And this algebra also satisfies some regularity property of KK theory. So from KK theory, this algebra is also very good. So this algebra is a nice object. From this construction, actually we are not just get this C star algebra. We actually get a pair of C star algebra. We have C star algebra A. This is a big, simple C star algebra. It's big. It's an ambient C star algebra. It's complicated, interesting, and then this C of X you start with. And this pair actually form a Cartan pair, or you can say this C of X inside A. Actually, it is a Cartan subalgebra. And if you look at this pair of C star algebras, actually you can recover a lot of dynamical information you start with. But I really want to look at the C star algebra A itself. And in general, if you look at a fixed C star algebra A, there may exist a lot of Cartan subalgebras, and they are not conjugated by automorphism and so on. Actually, they simply can fail to be isomorphic. So in general, Cartan subalgebra is highly non-unique. I will come back to this in a moment. Actually, the reason is not complicated. So this is the C star algebra we want to look at. And now if we look at this simple amenable UCT C star algebras, then we have this classification theorem. This theorem talk about, let's look at unital, simple, separable, amenable UCT C star algebras. let's talk about this condition in a moment. Then two C-star algebras are isomorphic if and only if they are invariant. They have same value of this invariant. And this invariant is called the Elliott invariant. Consists of the ordered K0 group, K1 group, the trace simplex, and the pairing between the trace simplex and the K ordered K0 group. So see, a 2C algebra isomorphic if and only if their skeleton, let's call this their invariant, their skeleton isomorphic. Those are abelian groups. This is the Shougai simplex. Then it's very possible in general. You just start with two very different topological dynamical systems. Say one is x1 gamma 1, one is x2 gamma 2. You look at the cross product, then you calculate their skeleton, the invariant. Then the invariant have the same value. Then they are isomorphic. But in general, so the value of the invariant is very much independent of this X and this group. You can have a very, very different dynamical system give you the same K theory, the K groups of the cross product algebra. And now you see that you can have isomorphic algebras, but then very different Cartan subalgebra. So in general, one should not hope to totally recover the dynamical information just by looking at the ambient algebra itself. Lots of information will get lost basically by the classification theorem. Now, let's forget about the complete recovery of the dynamical system. Now let's look at this condition. So for the classification theorem to work out, we really need this C-star algebra regularity condition. This is called Z absorbing or Z absorption condition. So what that is? This condition actually is a very, very C-star algebra regularity condition. Let's see what it is. Or what is this Z? This Z is actually called Jiangsu algebra Z. Then what is this C-star algebra? This C-star, the C-star algebra Z actually is an inductive limit of something called the dimension drop C-star algebra. And what is the dimension drop C-star algebra? It's the C-star algebra of continuous functions from 0, 1, from the interval to the tensor product, let's say M and Mn, M by M matrix algebra and N by N matrix algebra, you look at the tensor product, with the condition that the value of those continuous functions at one end, it belongs to one tensor factor, and at the other end, it belongs to the other tensor factor. So we have some boundary conditions. We are not looking at arbitrary continuous functions. This algebra is relatively easy to deal with. This type 1 algebra is very concrete, and it has lots of traces, lots of ideals, highly non-simple. But we can form an inductive limit of those dimension drop algebras so that if we look at this inductive limit, we make it simple. Such that the Elliott invariant of the limit algebra is isomorphic to the Elliott invariant of the complex numbers. Means that the K0 group is exactly Z. and the class of identity is exactly 1. And K1 is trivial, and it has a unique trace. So you can make it happen. It's not very straightforward, but you can make it happen. And actually, if you look at such inductive limit, it's unique. No matter which way you choose to get this inductive limit, they are always isomorphic. And this algebra is called the Jiangsu algebra, Xinghui Jiang and Hongbing Su. And then a C-star algebra is said to be Z absorbing if A tensor Z is isomorphic to A. You may say that why? Why we look at such thing? As I said, the K-theory of Z is isomorphic to C, the complex number C. If you calculate the invariant of A tensor Z, it's like you are looking at A tensor with a complex number C. It will change nothing. And if you work in the classification, then of course you should say, then you will think, then a natural thing to happen for this algebra, it should be A tensor Z is isomorphic to A, because they share the same value of the invariant because of this condition. Yes. Not like inductive limit. Yes, because this the building blocks are nuclear. Yes, this is. Yes, it is nuclear. You want some intrinsic. One way to say it, one way to do it is by this classification theorem. That's a unique C-star algebra covered by this classification theorem, then has the same invariant as C. Yeah, from this construction, of course, you will feel that this kind of artificial and so on. But it turns out it will get more interesting. There are many, many naturally arising C-star algebra satisfy this condition. You can verify it, and the Z absorbing can be characterized by using central sequences and so on. So maybe looks strange in the first place, but actually this is a very, very natural condition. Then the question is, okay, now let's look at this cross product algebra when this guy is Z absorbing. I mean, when the cross product algebra satisfies this condition, and now probably more related to your question, we start with this construction of Z, then look at Z absorbing everything in the context of C-star algebras. So this is really a C-star algebra property, but does it correspond to, well, in this case, look at this algebra, does it correspond to some property of the dynamical system you start with? So now let's try to answer these two questions, or in particular the second question. So here is the C-star algebra regularity property, and then what is the corresponding dynamical system property? Turns out that the property we want to consider is the mean topological dimension. This is the topological dynamical system property, and this mean dimension actually was introduced by Gromov and developed by Linden, Strauss, and Y's. So what is the mean dimension? Let's look at topological dynamical system. And let's start with just the topological dimension, the covering dimension. So we look at open cover. Then you can consider the order of the cover. So what is the order of the cover? You for each point x, you just can look the number of the open set above x. So the number of the layer above x. You let x change. You look the supremum. So you look the maximal number of the layers. Then subtract by 1. We want to normalize it. If it's a single layer, then it should correspond to 0. So the order should be 0. And in general, if you have an open cover, then sometimes there are some redundancy. Then you can look all possible refinement of your starting cover. Then look the order of your refinement. You try to throw away redundancy. You try to find out a most economical way to cover your space, but still under the approximation of the given cover U. Then the dimension or covering dimension of the space X is just is the least upper bound, so that no matter which open cover you start with, you always can find out the refinement so that the order is dominated by this number, and that's called the dimension of X. So this is just topological dimension. There is no dynamic. Now together with a group action, let's assume the group is the integer group. Then we can do the following. We still start with open cover U, but now because we have a group action, we can look at the translations of the open cover. So we look at the image of U, the image of the images, and so on. We look at the translations. Then we look at the common refinement. Then look at the degree or dimension of this open cover. This is still open cover of X. But in principle, the degree of this open cover can be huge, because you not just look at U, you also look at the translations. The open cover and the translations can be more or less independent. Then you take this average, this is where the mean comes in, and you let this n go further and further. Then this ratio, or this dimension grows, actually it converges. It converges to some number. Then you look at the supremum. You just look at all possible open cover. You look at this dimension grows. Then this is called the mean topological dimension. So nothing really special about Z. For any amenable group, you can use the Furner set to look at this averaging process. It converges. So the mean dimension is defined for actions of any discrete amenable group. So some remarks. If you start with a finite dimensional space, the mean dimension is always 0. The reason is that this common refinement, yes, it might be huge, but it's always an open cover of X. If the dimension of X is finite, then this D of such is uniformly bounded. If n go to infinity, of course, it goes to 0. But more interestingly, if the dynamical system is uniquely algorithmic, so suppose there is only one invariant probability measure, then the mean dimension has to be 0. I think this is interesting because the condition here is really matter theoretical condition. but the conclusion is in topological nature. Okay? So we will come back to this later. Actually, this is very important to us. Also, if the dynamical system has finite topological entropy, then the mean dimension is 0. Then here is the characterization. So here is the kind of the answer of of this question. So how can we relate this C-star algebra regularity property with some dynamical system regularity property? Turns out that they are equivalent. Let's look at ZD action. We can say something more general, but let's look at the ZD action. In this case, the C-star algebra is Z absorbing if and only if the mean dimension is 0. So on this side, this is the property of the ambient C-star algebra. Remember that the Cartan subalgebra is highly non-unique, but still it memorizes the ambient algebra, memorizes the 0 mean dimension. So yes, it's the Cartan subalgebra is highly non-unique, but it still memorizes something. So something really survived in this process. Well, in the rest of the talk, I'm going to talk the proof of this theorem, or roughly the idea of the proofs. So it will be more slightly more technical. I apologize in advance. So mean dimension Z absorbing. Why? Why is that? So here is roughly some idea that why there should be a connection. Z absorption, turns out that Z absorption is very, very close related to dimensions, or sometimes the comparison property of the C-star algebra. So what's a comparison we want to talk about? This is called the cones comparison. Let's look at a general C-star algebra A. Let's look at two positive elements. If you are not working on C-star algebra, you can think we are looking at the n by n, the algebra of n by n matrices, and let's look at two positive matrices. And now let's try to compare two positive matrices. How to compare it? How to compare them? We say that the element A is cone sub-equivalent to B. So A is dominated by B. If you are able to find out some sequence xn in the C-star algebra such that the cut down of this B converge to A. So in the matrix algebra case, what does this relation really talk about? It's just talk about A has a smaller rank than B. Because any positive matrix, you can have a diagonalization. You mix them into diagonal matrices. Then what does this relation talk about? It's just say that the diagonal matrix B has a more non-zero element. So that in the matrix case, that's roughly what you are talking about. But in general, it's more than that. That's the following. So yes, you have A is cones dominated by B, then the rank of A is going to be at most the rank of B. So this d tau is the rank function. It's in the matrix case, that's exactly the rank. But you really can talk about the rank function for general C-star algebra with traces. So you always have A is cones smaller than B, then the rank of A is smaller than the rank of B, but the converse in general is not true. In the matrix case, it is true. But for general C-star algebras, the converse is not true. Because look this side. This side is really talk about something is topologically dominated by B. But this side is talk about that measure theoretically A is small. The rank is really a measure. So in general, the converse is never true. But then here is a notation to talk about the failure, the degree of the failure of the converse. So yes, the converse in general is not true, but let's put some gap in between. If this gap is large enough, suppose there is a large enough gap so that the converse is true, then you write this gap there. You choose all such gap numbers, then you look at the infimum. This is something called the radius of comparison. Okay, so still, where is the dimension? Here is one example. Look, this is C-star algebras. The matrix value the continuous function on X. You try to come. What's that? Yes. Yes, this is the partial order. Yes. So now look at this algebra of the matrix value the continuous function on space X. You calculate this number. It's called radius of comparison. Then this radius of comparison is more or less this dimension ratio. More or less, I mean, it's in the error of plus minus, well, for safety. This 1/2 comes from the complex number C because all the algebra we are looking at over the complex number C, and the complex number C has a dimension 2 rather than 1. So look at this dimension ratio. This is the ratio between the topological dimension of X and the matricial dimension. But now go back to the definition of the mean dimension. This is a dimension ratio. So we are talking about the dimension of some open cover. We compare it with the size of the partial orbit. So this is a dimension ratio, or this is a dimension growth. And here is a similar thing. So this makes us think that there should be some connection. And in general, so why mean dimension 0? In general, here is a Tom-Winter conjecture. When a C-star algebra is Z absorbing, it's conjectured to happen if and only if the radius of comparison is 0. So in principle, Z absorbing should correspond to 0 to slow dimension growth, or 0 dimension ratio, slow dimension growth. So this ratio should be arbitrarily small. In principle, it corresponds to the Z absorbing, and now this should correspond to the 0 mean dimension. So that's roughly the motivation. It's not, it just comes from nowhere. There is a reason to think that this should be true. But to really get there, we have to use another property, or another dynamical system property, which is called the small boundary property. So what is that? Let's consider a pair of space X and a collection of Borel probability measures on X. And let's assume this collection delta is a closed set of the probability measures. Here are the motivating examples. So this property, small boundary property, was was from the dynamical system in the setting that we have a dynamical system X and gamma. Then canonically, you have this delta. Just choose it to be all the invariant probability measures. So you have X, then together with the invariant measures, not arbitrary measures, but you have this invariant measure. So in this setting, the small boundary property was introduced in 90s by Shu in the study of topological entropy. But in this formulation, you really can study small boundary property in a much more general setting. For example, if we look at C-star algebra and a commutative subalgebra, then you can't just talk about the small boundary property. Just look at this commutative subalgebra and look the traces comes from the big algebra, the ambient algebra. Then automatically you have such a pair of space and measures. So, okay, sorry, I have not really talked about small boundary property yet, but here it is. Suppose we have such a pair, X and delta. It has a small boundary property if whenever you have a point of the of your space, and whenever you have a neighborhood, then you will always be able to find out another neighborhood inside the given neighborhood. This neighborhood, let's assume it's closed, such that if you look at the boundary of your new neighborhood, then the boundary has measure 0 under all those measures. Small boundary means the boundary is small under all traces. It's 0 under all the trace in delta. So what's the connection with mean dimension and Z absorbing? First, the small boundary property corresponds to 0 mean dimension. The small boundary property implies the mean dimension 0 that is true for all amenable group actions. That's what showed by Linden, Strauss, and Weiss. Then in the Z or ZD case, you have the converse. Actually, they proved something weaker than this. It's not necessarily just free and minimal. Then which direction? Then in those cases, the mean dimension 0 also implies the small boundary property. So in principle, these two are equivalent. Although this is Goodman, Lindenstraw, and Tsukamoto. The relation with Z absorbing is that the small boundary property always implies Z absorbing. In this case, ZD action case, and also in some C-star algebra case. So now you see that to really show that Z absorbing is equivalent to mean dimension 0, the only thing missing is this implication. The Z absorbing should imply the small boundary property. So that's the only piece which is missing, and that's what we proved recently. So how to get there? How to get the small boundary property from Z absorbing? So small boundary property now it's really a property of the Cartan subalgebra, but Z absorbing is a property of the abstract ambient algebra. So how to get there? So let's look at small boundary property, and let's have a C-star algebra criterion. of this property as the following. So let's look at C-star algebra, and let's look a collection of traces. You can think we have a space X, then we have some delta, a collection of probability measures. Then you can look at this something called uniform trace norm. So you take an arbitrary element A, you look at AA star, then you look at the trace of AA star, then take a square root. But because you have, in principle, you have more than one traces, you look at all of them, then look at the supremum. This is called the uniform trace norm. And in the commutative case, this trace norm is just the L2 norm. You have a continuous function, you have some probability measure, then you just look at the L2 norm. But now the only thing is that you have more than one measures. You just look at all the L2 norm, then look at the supremum. That's the uniform trace norm. Now we can use this uniform trace norm to have a characterization of the small boundary property. Of course, in the setting of the commutative algebras. So this pair has the small boundary property if and only if for any continuous function on X, real valued. So basically, you are looking at a self-adjoint element in the algebra C of X. Then, also for any tolerance epsilon, then you are able to find out another continuous real-valued function G. First, this G approximate F in the uniform trace norm, up to epsilon. So you have an approximation, but more important, this G should be very good in the sense that you look at the zero side of the function G. It is uniformly small. And in the language of C-star algebras, you're basically talking about the neighborhood of the spectrum of G. Then it is uniformly small under all the traces. So the function f may have a large zero side, but you are able to approximate it using G with a very small zero side. And you really can characterize all of them using C-star algebras. I mean, forget about the zero side. This can be characterized by this estimation using traces and some functional calculus in C-star algebra. So why this is very helpful to us? Because recall that we really want to show this converse. Now we look at the ambient C-star algebra, which is assumed to be Z stable. Then for the ambient C-star algebra, this property, this characterization, those properties can be formulated just purely in terms of C-star algebras. Now let's summarize this property. Let's call it a property S. So a C-star algebra A is said to have a property S if whenever you have a self-adjoint element F and whenever you have a tolerance epsilon, you are able to approximate it by some element, self-adjoint element G, such that the neighborhood of the zero in the spectrum of G is uniformly small under all the trace measure. So you really have this property in terms of C-star algebras. No matter the C-star algebra is commutative or not, and more important, you have this property whenever the C-star algebra is Z stable. So this is very encouraging because whenever you have the algebra is Z stable, then it has this property. And this property really looks very similar to this, except that this property, the small boundary property, is really a property on the Cartan subalgebra. And this property S, this abstract analog of that property, is a property of the big ambient algebra. Yes, they look similar, but and this looks encouraging, but you still have to find a way to get to that Cartan subalgebra. I mean, in order to show that the Cartan subalgebra has a small boundary property by this theorem, you start with some continuous function f. You want to find out a g so that g has some neighborhood of 0 which is small and all traces. Okay, we can start with this lemma. Yes, we start with f in C of x. Then by this lemma, because A is the absorbing, we have some G has that property. Except one thing missing. This property just talk about the approximating element G is in A rather than in C of x. You start with something in C of x, but if you only use this property, you end up with something in A. It's not in C of x. And that's actually a very big problem. It's all the work about to overcome this. So what is the fix? So what is the fix? We introduce two more properties. And this is those two properties are really the properties of a pair of C-star algebra. So you have a C-star algebra A and you have a commutative subalgebra. You do not have to assume D is a Cartan subalgebra, just any unit of subalgebra. The first property, the property C, it's actually a property of relative comparison property. So suppose you have two continuous functions, f and g, inside D, inside this commutative subalgebra, and the rank of f is dominated by rank of g. Then you are able to twist f inside g. You can compare them. That's not something uncommon, but here we require something more. So how to twist it? We really require this element u to be something called almost normalizer. So you not only twist f inside g. If you start with arbitrary element in the commutative subalgebra, you should end up with something almost in the commutative subalgebra, in the trace norm. So we call them almost normalizer. So property C really talk about relative comparison property, but using almost normalizer. And then the other property E is some existence property, which says that whenever you have some element inside the big algebra, you are able to find out something in the commutative subalgebra so that they almost induce the same trace map. Then with these two properties, we can fix the problem. Assume property C and property E. If the ambient algebra has property S, then you can make the property S happen exactly inside the Cartan subalgebra. So then it has the property as the small boundary property. But you may ask when, well, I assume property C and E, when it happens. Well, in those cases, those two properties just hold. They really hold. And what is the proof? You use the Rockling property. And once you have a uniform Rockling property, then you can reduce the problem to this very concrete problem. You are looking at the matrix algebra over C of x as A. And what is D? Just the diagonal subalgebra. Then you have some very concrete algebra to work with, then there are some combinatoric, actually quite a few combinatoric, but you can show this property really holds. I run out of time, so this is the uniform Rockling property. This is basically the Rockling property, but not with respect to just one given invariant measure. It's with respect to every measures, and also relative comparison properties. Those properties turns out they always hold for ZD action and some other cases. Those are some pre-COVID result. And then with those properties, you can characterize the Z absorbing using small boundary property and property S and so on. And in fact, as a byproduct, you really get something more. The small boundary property, the characterization of the small boundary property actually is closely related to the real rank 0 of the sequence algebra. It's talk about the approximation of self-adjoint element using something is small near 0. So it can be characterized by the real rank zeros, and it also can be characterized by something called the uniform property gamma. So again, I'm going to skip some terminology. What is the uniform property gamma, and strong uniform property gamma, and so on. And here are some corollary. The line is that what you can say about a dynamical system by only looking at the big ambient algebra A. So first thing we can say is that if the trace simplex of A is a Bauer simplex, means that in this setting means that the collection of ergodic measures is closed, then you automatically has that the mean dimension is 0. Actually, you prove that what you get is that it has a small boundary property. It has property gamma, then it has small boundary properties, and so 0 mean dimension. And also, if the cross product algebra has real rank 0, means that every self-adjoint element can be approximated by invertible self-adjoint element, then automatically the algebra is Z stable, and the underlying dynamical system has a mean dimension 0. And also here is some cyst algebra corollary. So for the property uniform property gamma, it was conjectured for a while that if all the nuclear cyst algebra has a uniform property gamma, but as a corollary, there are some AH algebra which is not Jiangsu stable. Then it cannot have a uniform property gamma, because in that setting, uniform property gamma is shown to be equivalent to Z absorptions. So I stop here. Thank you very much.
Any questions or comments? The small boundary data as a closed subset of the set of traces on it, right?
Yeah.
My question is, why do you take the delta to be a closed subset?
Well, technically we need it. when we handle it, we really need it to be closed. Yeah, but for definition, you don't need. The pointwise convergence, the weak topology. Yes, certainly the weak topology.
Idea how you use the uniform Rockling property to reduce
case of matrix algorithm, see if that's
Yes.
slide.
Let me see if on some skipped. Yeah, this. So what is the uniform Rockling property? Maybe I use. So it talk about this space X. Then you always be able to find out towers, the Rockling towers. Yes. This is you always be able to find out towers, such that the leftover is very small and uniformly small, and all traces. But what does those towers talk about? If you have let's say the base space is Z, then for this tower it corresponds, well, this is the open side. It corresponds to C0 of Z. But then together with the translation, what you have, so from this whole tower, you get a matrix algebra over the base. And those level set together, it's the diagonal subalgebra inside here. Because all we care under the trace norm. So the leftover is small, it's just a small. So that's roughly, you reduce the problem of the whole space into the towers, which just corresponds to matrix algebra over the basis.
Size of the matrix algorithm, that the height.
Yes.